This is section 6.1, areas between curves, and our one and only objective for the section is to find areas between curves by using integration. When we're done, I'd like you to be able to explain how you will decide whether to create a sample strip that is vertical or a sample strip that is horizontal. And I want you to think about the issues that you'll need to keep in mind as you are making your decision. So first of all, let's connect to our old knowledge and recall that the limit of a Riemann sum, or a definite integral, will equal the area between a curve and the x-axis if the curve has positive outputs. We can extend this idea to cover any area between any two curves by using the fact that finding the infinite sum of an infinite number of sample strips areas will result in the total area of a region. So we've got some steps to keep in mind as we go through these problems. The first is you need to graph the boundary curves at all times. You've got to graph them so that you know what's on top and what's on bottom, or which is to the right or which is to the left. The next step, step 2, is you need to determine the coordinates of all your intersections. This is critical because those coordinates are what will become the upper and lower limits on your integrals. Step 3, you need to decide which direction the sample strip should be drawn and how many strips you will need. We'll get into the nuances of this step as we do the examples. Step 4, once you've drawn that sample strip, you need to label the endpoints with the correct variable. This is essential for setting up your integrals, and it will come into play again in section 6.2 and 6.3, so you need to develop the habit now. The variable you will use will always, no exceptions, always be the variable whose axis is perpendicular to your strip. That means if you've drawn a vertical strip, you will use X's to label your endpoints. If you've drawn a horizontal strip, you will use Y's to label your endpoints. Lastly, you will set up and evaluate an integral of the form, the integral from the low X or Y coordinate up to the high X or Y coordinate of the length of the strip times the thickness of the strip. And the thickness will either be a dx if you've drawn a vertical strip, or it will be dy if you've drawn a horizontal strip. And your area integrals will always take this form. With example 1, we want to follow the steps, and our first step is to graph the boundary curves. Now, I've already done that for you, so our second step is to determine the coordinates of all intersections. Now, because I graphed this on a nice computer program, we can just read the intersections off and see that they're -1, 1 and +2, -2. But let's say, for the sake of argument, that you are a terrible grapher and that you don't ever keep your grids drawn to scale, and so it's really hard for you to read intersections off of a graph. Well, the other way to find these intersections is to actually solve the system. If I want to figure out when y equals 2 minus x squared is the same as y equals -x, I can solve using substitution and replace y with a -x. And then I can use my algebraic techniques to isolate x. Now, because I have a square and a linear, I'm going to have to move everything to the same side and then factor. When I do that, I can see that x is +2 and x is -1, and then I can plug those into either equation to get the y coordinates. Now, once we have the intersections, we're ready to move to step 3, which is to decide which direction the sample strip should be drawn and how many strips I'm going to need. Now, some of the things you want to keep in mind as you're making this decision is, first of all, is it easy to isolate either y in both equations or x in both equations? In this particular scenario, we can see that we have y in terms of x and we have y in terms of x already. We could isolate x in both if we wanted, but that would create more work. So because y is already given to us in terms of x, it's going to be easier for us to just draw our sample strip so that everything will be in terms of x. So if we look at step 4, we're going to draw the sample strip and label the endpoints with the correct variable. And the variable that we will use is always the variable whose axis we are perpendicular to. So here this strip is perpendicular to x. That means we're going to label the endpoints of this strip using x. Another way to help make that decision is you look at these 2 points and you figure out which coordinate is shared. What coordinate is the same on this point as it is on this point? And the answer is they have the same x x value. So we put x for the x-coordinate, and then the y-coordinate will come from the curve upon which that point lies. So since this point is on the parabola, we're going to replace y with a 2 minus x squared. Similarly, down here, we will replace that y-coordinate with what it equals on this curve, y equals negative x. Now, the reason we want to do that is because our goal is to write the area of this strip, because that area will represent the area of all of the strips. So inside our integral, we will have the length of that strip times the thickness of the strip. Well, the thickness of the strip is a tiny, tiny, tiny bit of horizontal length, which is going to be a little piece of the x-axis. And the length of that strip is a vertical distance, so it's a difference between y-coordinates. So we'll take the top y-coordinate minus the bottom y-coordinate, and we'll have a 2 minus an x squared minus a negative x. Now, as far as the limits go, we are looking for the furthest left this strip can go. Because everything is in terms of x, we want the smallest x value that we can get in the entire shaded region. So the smallest left x value is a negative 1, and the largest x value is a positive 2. So we think about how far left we can drag that strip and how far right we can drag that strip. And we see here now that we've created an integral in terms of x that we can now use the fundamental theorem of calculus part 2 to evaluate. So to do that, we're going to simplify the integrand, and then we're going to answer the question posed by the integral symbol. And that is, what did I take the derivative of with respect to x that gave me this inside? And that's a 2x minus an x cubed over a 3 plus an x squared over a 2. Then I'm going to evaluate this from negative 1 to 2, which means I plug the top number in first, and then I subtract what I get when I plug the bottom number in. Bottom number is a negative 2 plus a 1/3 plus a 1/2. If I now combine everything, I'll have a 4 plus a 2, that's a 6. Have a negative 8/3 minus a 1/3, that's a negative 3. And then I have plus a 2 minus a 1/2, which is plus a 1.5. So it looks like I've got 7.5 minus 3, that's 4.5, or 9/2. With example 2 now, we again have two curves, one of which is y squared and the other which is y cubed, and we want to find the intersection points. So here we can see from my picture that it is 1, 1 and 0, 0. Again, we could solve the system analytically by doing a substitution and figuring out when y squared is the same as y cubed, or rather when y cubed minus y squared equals 0, or y squared times y minus 1 equals 0, and that happens when y is 1 or y is 0. Either of those would work, and we get our points. Once we have the points, we need to decide which direction we're going to use to draw our strip. So our strip in this case, if we look, we can see that x has been isolated. Because x is already in terms of y, it might be easier this time to label and draw things that go horizontally. So in this case, if we now want to label the strip, we're thinking about the coordinate that these two share. They share a y-coordinate. So we'll put the y-coordinate as y's, and then we need to get x's in terms of y. So on this first curve, we need to know what is x in terms of y, and same thing with the second one. Now notice that I did not label the curves because I want you to know which one is which. How do we decide whether this is the y squared curve or if this is the y cubed curve? To help determine, let's think about a y-coordinate of a half. If I have a half and I square it, it will turn into a 1/4. Whereas if I cube it, it will turn into a 1/8. So horizontally, which one is bigger, the 1/4 or the 1/8? Hopefully you know that it's the 1/4, which is larger, so that means that squaring it is going to move me further to the right than cubing it. Once I've labeled my strip, now I can find the length of that strip. Well, the length of this strip is a horizontal distance. So because it is horizontal, that means it is a difference between y coordinates. And to get that length as a positive number, we will need to take the right x coordinate minus the left x coordinate. So that's going to be a y squared minus a y cubed. the width of this strip is going to be a little tiny bit of the y-axis, which will be dy. To get our limits now, we're going to drag this as far down and as far up as possible. If I drag it down, I have a limit of 0. If I drag it up, my biggest y-coordinate is a 1. Once we've set it up, we can answer the question, what did I take the derivative of with respect to y that gave me a y squared? That's a y cubed over 3. And then what did I take the derivative of with respect to y that gave me a y cubed? That's a y to the 4th over 4. Evaluate from 0 to 1, and we'll get a 1/3 minus a 1/4 minus a 0. Well, that is a 4/12 minus 3/12 gives me 1/12. So I'm going to do example 2 again using a slice that goes the other direction. And the reason I'm going to do this is because it shows you the flexibility that you can have. We still have the same boundary curves, x equals y squared and x equals y cubed. We still have the same intersections, 0, 0 and 1, 1, except this time instead of drawing a horizontal strip, I'm going to draw a vertical strip. Now when I draw a vertical strip, then everything needs to be in terms of the axis that I'm perpendicular to, which is an x. So I will see that I have a same x coordinate for both of these strips, so I can put an x. And now I need to get the y coordinates in terms of x. That means I need to go to my curve and I need to isolate my y's. For this one, I'll get plus or minus the square root of x, or I'll get the cube root of x. We can see here that since y is plus or minus square root of x, we need to decide whether we have the positive root or the negative root. Well, since the outputs on the square root curve are above the x-axis, that means we're working with the positive output. On this one, there's only the cube root of x as an option. So now if I want to write the area of that strip and then add them all up, I will get the integral from the smallest x value, which is 0, to the smallest or the largest x value, which is 1. So furthest left I can drag that strip, furthest right I can drag that strip, and I will take the length of this strip, which is the top y coordinate minus the bottom y coordinate times the thickness of the strip. Notice now, if I use Fundamental Theorem of Calculus Part 2, I will answer the question, what did I take the derivative of with respect to x that gave me this? And that would be x to the 4/3 divided by 4/3 minus x to the 3/2 divided by 3/2, evaluated from 0 to 1. If I plug in 1, I get a 3/4 minus a 2/3, and if I plug in 0, I get the same thing. Get a common denominator, I'll get 9/12 minus 8/12 gives me the exact same number that I had before. Notice that I could have sliced either direction, and as long as I label things with the proper variables, I will get the same answer. So let's look at example 3 now. I want to find the area of the region enclosed by y equals 0, which is this horizontal line, y equals x squared, which is the parabola, and x plus y equals 2, which is this line. I graph the region, and then the next thing I do is I find the intersections. I can see that 0, 0 and 2, 0 are both intersections here, and up here I've got an intersection of 1, 1. We can double check that 1 gives me a 1 out and 1, 1 gives me the 2. So now I'm at the crossroads. I have to decide would I rather cut vertically or horizontally. And you'll notice in your notes that I've drawn 2 versions of this, so we're going to do it both ways. Let's say I want to cut vertically. If I cut vertically, I have to draw a representative slice that works for the entire region. If I draw a slice here, notice that the top is on this parabola, the top point. And that will be the case as I move that strip through the region until it hits this intersection point. And once I hit this intersection, then I jump tracks. The top point is no longer on the parabola, it jumps to the line. So that means I'm going to have to draw a second strip in order to continue through the rest of the region. What that means for me is that I'm going to have 2 integrals set up. So the first integral is going to represent this region on the left until we hit that intersection. So its limits will go from pulling it all the way to the left, which is 0, and all the way to the intersection, which is an x value of 1. And then I'll pick up over here, and this strip will start at the intersection, which is 1, and it will continue all the way to the right to its x-coordinate, which is 2. Now, in order to write the areas of these strips so that I can add them all up and get the area of the entire region, I need to label the endpoints in terms of the variable that the strip is perpendicular to. So in this case, these two share an x-coordinate. The y-coordinate will come from the curve that we're sitting on. So in this case, the y-coordinate is x squared. On this one, the y-coordinate is always 0. So the length of this strip is the top y-coordinate minus the bottom y-coordinate, which is x squared minus 0, and the thickness of the strip is dx. On this one over here, again, we need to label. The x-coordinate is the same for both. The y-coordinate comes from the curve that we're on. So on this bottom one, we get a 0. For the top one, we now have to work with this just a little bit. We need to isolate the y because we need y to be written in terms of x. So we'll have y is 2 minus x. Now the length of that strip is a 2 minus x minus a 0. We took the top y-coordinate minus the bottom y-coordinate. And the thickness of that strip is simply dx. Now if we answer the question posed by these symbols using the fundamental theorem of calculus part 2, we'll get an x cubed over 3 evaluated from 0 to 1 plus a 2x minus an x squared over 2 evaluated from 1 to 2. Evaluate and we get 1/3 minus 0 plus, plug in the 2, that gives us a 4 minus a 2, subtract what we get when we plug in a 1, that's a 2 minus a half. Put this all together, 4 minus 2 minus 2, that gives us nothing. We have a third plus a half gives us 5/6. So now let's do it the other way. Instead of cutting vertically, let's cut horizontally. When we cut horizontally, the benefit that we see is that as I move this strip through the entire region, the left dot never jumps tracks. We always stay on the parabola, and the right point always stays on this equation of the line. So it too never jumps tracks. So that means if I set up my area in terms of y, I will only need one integral. That in and of itself is enough to maybe convince you to do everything in terms of y. So if we start labeling the points now, we can see that the y-coordinate is shared by both points. The x-coordinate is going to come from the curve that we are on. So if we look here, remember this curve was y equals x squared. The goal is to get everything labeled in terms of y because that is the axis that our strip is perpendicular to, and it is also the coordinate that is shared. So if I isolate x here, I'll get x equals plus or minus square root of y. We have to decide, are we on the positive side of the parabola or are we on the negative side? And hopefully you see that we're on the positive because the x-coordinate is a positive, so we'll use the positive root. On this one, remember the curve was x plus y equals 2. So in this case, we're going to be isolating the x instead of the y. That will give us 2 minus y, and we can now find the length of this strip. It is a horizontal distance, so it's a right x-coordinate minus a left x-coordinate. So we'll get a 2 minus a y minus a root y. The thickness will be dy, and the limits will come from the lowest y-coordinate that we can hit, which is 0, and the largest y-coordinate that we can hit, which is 1. Evaluate this using the fundamental theorem of calculus and answer the question posed by this symbol. What did I take the derivative of with respect to y? They gave me the inside, and it's 2y minus y squared over 2 minus y to the 3 halves divided by 3 halves, evaluated from 0 to 1. Plug in 1, you get a 2 minus a half minus a 2/3. Plug in a 0, you get a 0. Put this all together, we get 5/6. Notice we got the exact same answer as when we cut it vertically, only this time we only had one integral to use. So example 4 now, we want to find the area in the first quadrant bounded by the curves y equals x minus 2 and y equals the square root of x. And you'll see that I gave you 3 versions. That's because we're going to do 3 different techniques to find this area. First and foremost for all 3 of these is after we've drawn the curve, we need to label the intersections. I will trust that you can find these intersections using algebra if necessary, so I won't spend time on the video going through that. On the first one, let's cut vertically. If you cut vertically, notice that you're going to need 2 strips, and the reason you're going to need 2 strips is because as you drag this strip through the region, when you hit this intersection, the bottom point will have to jump tracks. It will come off of the y equals 0 and jump onto the line. So we need 2 integrals and 2 strips, and both will be labeled in terms of x. So to get the y coordinates on all 4 of these, we need to think about the curve that we're on. For this bottom point here, in this region, we are always going to be on y equals 0. The top one is always on the parabola, which is the square root of x, sideways parabola, I should say. For this one, the top is still on that sideways parabola, whereas the bottom is now on the line. Since we're doing everything in terms of x, we need y to be isolated, and it already is. So now we can set up area in terms of x will be the first integral, which is the length of this strip, which is the y coordinate minus the y coordinate times the thickness, and its limits will be as far left, which is 0, and as far right, which is the intersection. Then we will add the area from the second. So the area of this second strip is going to be the top y coordinate minus the bottom y coordinate, and the thickness will be dx, and we will integrate from its furthest left, which occurs at the intersection, and its furthest right, which is the x coordinate of 4. So here's our setup for the area in terms of x. We can also set up an area in terms of y. If I set it up in terms of y, that means I will cut horizontally. Now notice when I cut horizontally that I'm only going to need 1 integral. I need 1 integral because as this strip moves up and down through the region, the left point never gets off of that square root of x curve, and the right never gets off of the line. So because we never jump tracks, we only need 1 integral. Now in order to set up the integral, we have to label the points, and because that strip is perpendicular to the y-axis, everything will be in terms of y. That means we need to go back to the curves and isolate x. So in this case, x is going to be y plus 2, and in this case, x will be y squared. So this x coordinate is y squared. This one is a y plus 2. If I now set up the length of that strip, it is the right x coordinate minus the left x coordinate. So y plus 2 minus a y squared with respect to y, and I will integrate from as far down, the lowest y value that I have, which is 0, up to the highest y value I have, which is 2. I will trust that you can compute these using the fundamental theorem of calculus part 2, and you'll find that no matter which one you use, you will get 10/3 as your answer. So the last method we're going to use for this 4th and final example is sometimes we can use the geometry of the figure. And we can see here that this area, this region that is trapped in the first quadrant by these 2 curves, is the same as this entire area minus the triangle. So if we write the entire area using what we knew before, which is just the integral from 0 to 4 under this curve, which is root x, and then simply subtract the triangle's area, which is 1/2 its base, which is 2, times its height, which is 2, then we will end up getting that same 10/3. So the upshot of this particular example 4 is that you will almost always have options, and your job is to figure out which option is going to be the most efficient, will require the fewest number of integrals, and which will save you time. So I want you to think about that as you answer the language objective question for this section.